everyone, welcome to Vedantu J English. I'm Diksha Kaushal, your chemistry master teacher. So everybody do let me know in the chat box if I am clearly visible and audible to all of you or not. Yes students, am I visible, am I audible to all of you or not? Do let me know in the chat box. Hi everyone, welcome to Vedantu. So that we can start with the session. Yes students. Am I visible? Am I audible? So let's start the session without wasting any time. Right, so guys, in the last class, what we did? In the last class, we discussed about overlapping, VBT. Today, I'm going to discuss about hybridization, right? So it's going to be a very short session because my health was not fine yesterday. Right, I needed break, so that's why I ended the class at overlapping only. But today we are going to cover all the topics that you need to know to understand the next lecture, that is going to be VBT and Vesper theory. Okay, now let's understand this. Before that, guys, the homework, I hope so you guys have done the homework. The answer is the correct order of overlapping extent of axial overlapping is PP, then SP, then SS. That is the correct answer. C is the correct answer here. Right. Now let's talk about overlapping. Like what are the there's just one topic that was left in overlapping. Let's discuss about that. That was in phase and out of phase overlapping. Right. So when orbitals of two atoms come close to make a bond, they overlap. Overlap can be positive, negative or zero depending upon the direction of the wave. Now, if you talk about the direction, let's talk about that. These signs, right, will represent it by positive and negative. Do you remember when we used to draw waves, right? How we draw the waves? We draw it like this. This is positive, 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 negative, negative, negative. That does not mean that its charge is positive or this is negative. It has no relation with the charge. These positive and negative are telling you that these are the phase, right? These are the phases, right? Show signs, phase of the orbital wave function not related to the charge in any case, right? So now if you talk about positive and negative, positive will be in phase overlapping, negative is out of phase overlapping. Let's discuss this with the help of diagrams, right? So when you talk about positive overlap, right, this is in phase or positive overlap. This is out of phase or negative overlap. Do you remember constructive and destructive wave functions when we discussed about structure of atom? So when two positive things combine, constructive things is happening. When one positive and when negative are combining, destructive interference we call it. This you must have studied in physics, right? In the similar ground, when you have two lobes which are positive, right? When they are combining, we say that this is in phase, it is positive, right? And when you have one positive and one negative, that is out of phase or negative. Similarly here, two positive, one P and one S, it is in phase. One negative, one positive, it is out of phase, right? Next examples are in sideways overlapping. You will see in this also, this one is positive, this is in phase and this one is out of phase, out phase. When two positives are overlapping, that is in phase, two positive, two negative are overlapping. When one positive, one negative, one negative, one positive are overlapping, that is out of phase overlapping, right? Now let's talk about zero overlapping, right? Zero overlapping means they will not overlap only. Let's forget about positive or negative. They will not overlap. Thank you so much, Jay, Supriya. Thank you so much for your wishes. Thank you so much. Right? Happy Teachers Day to you as well, because you guys are what makes us teachers, isn't it? So, zero overlapping is when there is no overlap. Now, for example, you talk about Py and s orbital, they will not have any overlapping. Px and s can overlap. Pz can this can overlap like this. Even Py and s can overlap like this. This will be overlapping. But if you have, this is Py and this is s, they will not overlap like this, right? Why? Because in reality, it is like this. Here, this is the lobe, this is the lobe, this is p orbital, right? Which we actually write like this, okay? And this is s. So that's why they will not overlap, right? So that is zero overlapping. If you talk about one px and py, this is py and pz, right? So this is py in this direction, pz is in this direction, and that is the reason they will also not overlap with each other. They will not overlap, there will be zero overlapping here. Thank you MJ. So this is called zero overlapping, right? This is a criteria of zero overlapping, and overlapping is done here, right? That's it about overlapping. Rest of the part we have discussed in the previous lecture. Now let's talk about, let's talk about hybridization. If you talk about hybridization, right, what is the phenomena here? Let's discuss. So I'll tell you why we need hybridization. So simple thing is, if you talk about CH4, molecule, right, carbon you have, right, carbon is atomic number 6, that is 1s2, 2s2, 2p2, right. Now if you see this here, this is 1s, this is 2s, this is 2p. In the ground state it is 1s2, 2s2 and this is 2p. Now according to this, carbon should make only 2 bonds, but in reality we know that carbon makes 4 bonds, so that means excitation will happen here. So this electron is going to get excited, so the excited state is going to be like this, 1, 2, this is 1, 2, 3, 4. And as we discussed in the last class when I taught you covalency, right, I taught you there that these are the 4 bonds. So here what you will see, 4 covalent bonds you will see here, isn't it? 4 covalent bonds you will see here. So according to this theory, right, if I talk about this thing here, according to this theory, what should happen here? What should happen? According to this theory, one overlap, if let's talk about hydrogen, okay, here I am talking about hydrogen. Hydrogen is 1s1. So each hydrogen here will have 1s1 electron. Let's say here because for overlapping we need half-filled orbitals with opposite spins. So that means when the overlapping is happening, if let's say this is carbon, it has 4 orbitals, it has 1 s orbital and it has 3 p orbital. One is this one, how do I write it? Let's say this is px, this is py and this is pz. Okay, these are the 3 p orbitals and it has 1 s orbital. Okay, these orbitals are combining with hydrogen. So this px orbital, this is px, this is px. Or you know what I'll do? One by one I'll draw that, okay? Let's say this is px. Now this px is overlapping with the orbital of hydrogen, right? And it is making 1 sigma bond, right? This is py. This py is overlapping with the orbital of hydrogen and it is making another bond. Now let's say you have pz, right? Now this is overlapping with another orbital of hydrogen and it is making the third bond. Now till now I have made 3 bonds of p, right? I am left with s orbital. So what I'll do, let's say s orbital is this one, this is s orbital and that's how it is making one bond, right? Okay, with the s orbital. So what we are saying here, what we are discussing here, that here what will happen, these four, how they will make the bond, how they are going to make the bond. How they are going to make the bond. That means I am saying that it will be like this, 1, 2, 3, 4. It is going to make a bond, this with 1s of hydrogen, 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 right? Okay. So that means, can you tell me how many bonds in total it will have? It will have 4 bonds. First bond will be between 2s of hydrogen, 2s of carbon with 1s of hydrogen. Then bond will be between 2p of carbon and 1s of hydrogen. Then 2p of carbon, 1s of hydrogen. Then another will be 2p of carbon and 1s of hydrogen. So that means these 3 bonds are same. This one is different. So that means in CH4 what should happen? Right? According to this theory, in CH4 what should happen? In CH4, right, 4 bonds we have. 3 bonds should be same. Let's say this is a bond of C and H where you are using carbon 2s and hydrogen 1s. Rest of the bonds, let's say, are between 2p of carbon and 1s of hydrogen. So that means according to this theory, according to this, 3 bonds should be same, 1 is different, 1 is different. According to this theory, this should happen. But this is not the reality. This is not the reality. This is not the reality. If I am saying this is not the reality, that means there is something else, and that something else we call hybridization. What we call it? Hybridization, right? Okay, you understood? Because this is not the reality. All the 4 bonds are, all four sigma bonds are same. Sigma bonds have same bond length and bond energy. So if they have same bond length and bond energy, that means something we are missing here, and that hybridization is going to clear that up. Thank you, Premlata. Okay, so hybridization is going to clear this particular fact. Now tell me, do you understand why we need hybridization? What is the need of hybridization? Why can't we directly start VBT? In fact, this is a part of VBT only, right? Okay, everybody. Now let's see. Now understanding hybridization will be very easy for you. So hybridization is needed for us because phenomena of intermixing of atomic orbital. Hybridization is, for example, you have this yellow color bucket, you have this blue color bucket, you have this green color bucket. Okay, you mix them together, and you have a bucket which is, let's say, I don't know, after mixing what will be formed. Let's say pink color is formed. So after mixing these 3 buckets, you will have these 3, right? Now what you will do, instead of making 1, you divide it into the 3 same buckets. Now you have 3 same buckets of pink color, right? In one bucket you have yellow, one bucket you have blue, one bucket you have green. If you are intermixing them, right, you'll mix them in a big bucket, then you will divide it into those small buckets, and now after intermixing in those 3 buckets, you will have the same color, right? Same thing is hybridization. phenomena of intermixing of atomic orbitals. When you intermix the atomic orbitals of same or nearly same energy. What is written here? Same or nearly same energy. Like if you want to intermix 1s with 3p, it's not possible, right? 1s and 3p intermixing is not possible. 1s and 2s intermixing is possible, right? But why would you do that, right? Chalo, let's say you have 2s and 2p intermixing is possible, but 3p and 4p intermixing not possible. So you need to see that the orbitals has to be same or nearly same energy, giving rise to hybrid orbitals. Now the orbitals that you form is hybrid orbitals, and these are hybrid orbital, like they are of the same color. Similarly, they will be of the same energy, right? They will be of the same energy and same shape, and is called hybridization, right? So one by one we are going to see the examples to understand this concept better. So if you talk about the salient features of hybridization, the number of hybrid orbital is equals to the number of atomic orbitals hybridized. For example, these all things are directly from your NCERT, okay? So number of hybrid orbitals is equal to number of atomic orbitals being hybridized. So if you are mixing, let's say 1 plus 1 plus 1, then you will have 3. It's not like you are mixing S plus P, then you will have sp3. Not possible. If you are mixing 3 orbitals, you will have answer will be 3 only. That means you will have sp2, 1 plus 2, that is 3 only. So if you are mixing, so simple thing is, if I am mixing 1s and 2p, right, I will have sp2 because 1s and 2p, and these sp2 orbitals will be 3. 3 sp2 orbitals I'll have, right? If I am mixing s plus p plus p plus p, then I'll have 4 sp3 orbitals, right? If I am mixing S and P, I will have 2 sp orbitals, right? Hybrid orbitals are always equivalent in energy and space. So that's why what I am writing here, I am writing here 2 sp. So 2 orbitals are formed which are same. Here 3 sp2 orbitals. 3 orbitals are formed and they are same in energy and shape. 4 orbitals are formed and all of them are sp3. Okay. Mostly we are going to discuss about sp, sp2 and sp3 in today's session, right? Hybrid orbitals form more stable bonds compared to pure orbitals. See, everything in chemistry is in the world is happening because to attain the stability. If it is getting into an unstable state, it would never combine, it would never do hybridization. It is doing intermixing just to be more stable. So hybrid orbitals are more stable than individual p and s orbitals, right? Then hybrid orbitals are directed in space in some preferred direction to have minimum repulsion. Usually we represent it like this, one small lobe and one big lobe. This is how hybrid orbitals are represented. Minimum repulsion between the electron pairs, right? And you know, we'll discuss about shapes, we'll discuss about geometries, right? This will give rise to geometry or shape of the shape. We'll discuss later on what is the difference in shape and geometry. But why you will see some orbitals have trigonal planar shape, all these things you will discuss. Trigonal planar, tetrahedral, trigonal bipyramidal, linear shape, then you have octahedral shape. Why you have different geometries and shapes? Reason being why we have these different shapes and geometries, because in this, these hybrid orbitals, they combine there. So for example, you have 3 hybrid orbitals. You know how they will combine? How they will actually combine with each other? Like this. Can you say what kind of shape they are making? They are making a trigonal planar shape. So you can see if you have something like this, it will exist like this. A, B, B and B. This is giving rise to a specific shape that is trigonal plane. I am just giving you one example here. We are going to discuss about all the shapes and geometries, don't worry, right? So why these geometries, specific geometries we have? Because of hybridization. Repulsion between electron pairs, this is stable arrangement. Therefore, the type of hybridization indicates the geometry. Why we are discussing these hybridization? Because these hybridization are going to tell us about the geometry, right? Then, what are the conditions for intermixing? First condition is orbitals must have same or nearly same energy, right? So what they should have? They should have same or nearly same energy, only then it is possible for them to do hybridization. Excitation of electron is not necessary priority to hybridization. It's sometimes without getting excited, they can do hybridization, right? So it's not that important. If it is needed, they will excite. If it is not needed, it will not excite. Only the orbitals present in valence shell can participate. Only valence shell. Just like in overlapping also, only valence shell orbitals were participating. Same. In hybridization also, only valence shell orbitals will participate. Right? It is not necessary that only half-filled orbitals participate in hybridization. In some cases, even filled orbitals can take part in the hybridization, right? Even filled orbitals, these are some exceptions that we will discuss, right? That sometimes even the filled orbitals which have 2 electrons, they can also take part in the hybridization. This last point, we'll discuss this later on in this chapter, right? Okay, understood? Yes, everybody. So, one by one, we'll discuss about SP, SP2 and SP3, right? So, SP is the type of hybridization involves the intermixing of one s and one p orbital, resulting in the formation of 2 equivalent sp hybrid orbitals. Such a molecule in which central metal atom is sp hybridized linked directly to other 2 atoms possess linear geometry. That means if you have sp hybridized, it will give you linear geometry. Linear geometry. Now let's understand this with the help of an example, right? Let's understand this with the help of an example in ethyne. Chalo. Let's discuss about that, right? Ethyne. Which bond should we discuss? Ethyne, let's discuss that, okay? This is the compound which shows sp hybridization, right? Or shall we discuss about sp3 firstly? That would have been easy. But let's discuss about sp firstly, now that we have landed here. Carbon is 1s2, 2s2, 2p2, right? If I excite the electrons, because carbon is tetrahedral, so I need to excite the electrons. So in the ground state, and this is, let's say, the excited state, here the electrons will be 1, 2, 1, 2, 1, 2. And in the excited state, it will be 1, 2, 1, 2, 1, 2. Okay, that is how it is going to be. This is the ground state, this is the excited state. Now guys, see, if this is the ground state, this is the excited state, a very simple thing here that we are going to do. In the excited state, you have 4 orbitals, right? Now understand one thing. Here what will happen? Right here, what will happen? You will have 2 hydrogens only here, right? So in this case, you know what will happen? In this case, what will happen? These 2, 1s and 1 of P. Any of two will get hybridized. This is for a triple bond what happens, okay? Any of two will get hybridized. So you will have two sp orbitals that will be formed here, right? And rest two will remain as it is. So what will happen here? This is the carbon. In carbon you will have two sp hybridized orbitals. So this will be the first sp hybridized. This will be the second sp hybridized. So I'll just draw it like this. This will be the, let's draw it on the next page only, right? So here what will happen, you will have two sp hybridized, this is carbon, this is carbon. You will have two sp hybridized orbital, one sp, other sp, and here also it will show you one sp and this is the other sp, okay? Two sp hybridized orbitals it has. Because it is going to give you linear shape, so that's why I have make it as linear shape. So now this will combine, and here this sp and this sp are going to combine, give you sigma bond. This will give you sigma bond. This sp and one of hydrogen, 1s of hydrogen will combine and they will give you a sigma bond. This will give you a sigma bond here, a sigma bond here. Right? Now what will happen, there will be rest, will have py and pz also. This is py, this is pz, that is also remaining. So you will have py here, you will have py here, and this py and py are going to do sideways overlapping, right? And it is going to form a pi bond, right? Then there will be one more, that is pz and pz, right? And these two pz orbitals are also going to do overlapping and give you another, I can also show it here, another pi bond. And that is why you have, in this you have one sigma and two pi bonds. This is sigma and this is also sigma. Okay, so that is the structure of hybridization for sp hybridized orbital, right? Okay. Gaming, if you're asking me what is valence shell, then I think you're on the wrong maybe you are in the wrong class, or maybe you're on the wrong platform, right? Or maybe you're on a wrong video, right? You need to watch this lecture from the starting, right? So that is how this exists, right? So these are in BeCl2 also, same thing will happen, right? So in BeCl2 also sp and sp are combining. As you can see, this one is sp and this one is another sp. They will combine with the p orbital of chlorine, right? So basically what is happening here, right? You have Be, 1s2, 2s2, right? Now what will happen here, when they get into the excited state, they will form this kind of situation, okay? In this state they have this thing, in the excited state, two electrons here, 1 and 1 here, and this S and P is going to combine to give you two sp hybridized orbitals, okay? This S and P is going to give you two sp hybridized orbitals, right? Okay. Now let's talk about sp2, which is going to give us trigonal planar geometry. Let's talk about what is trigonal planar geometry. In this hybridization, there is involvement of 1s and 2p orbitals, right? And this is going to give you sp2 hybridization, and this is oriented towards giving you trigonal planar geometry, right? Okay. Trigonal planar geometry. Geometries we'll talk about later on this chapter again also, right? So let's talk about sp2 hybridization. This is in case of ethene. You can say CH2 double bond CH2. Let's see how it is formed. So when you talk about carbon, again it is 1s2, 2s2, 2p2, right? And I'm just directly going to write the excited state now. Okay, and outermost orbital only we are discussing here. 1, 2, 3, 4. Right? Excited state I am directly writing. This is the excited state. Now if you see this here, what will happen? This S and this is P, this is 2S, this is 2P, this is 1S. 1S is not going to take part. 2S and 2P are going to take part. And this 1S and 2P orbital is going to form you sp2 orbitals. And here it is going to form 3 sp2 orbitals. Right? 3 sp2 orbitals plus 1 unhybridized. Plus you will have 1 unhybridized PZ, PY or PZ, anything you can write. I am writing, let's say, PZ. Okay, anything you can write. You just need to have a sideways overlapping. Right? So by this what will happen? How it is going to form? This is carbon, this is carbon. Now because of 3 sp2 hybridized, they are going to form a trigonal planar geometry. So this is 1, this is 2 and this one is 3. This is 3 hybridized. This one is also, let me just write it here. This is 1, this is 2, no, it will be like this. This is 1, this is 2 and this one is 3. Okay, that is how we are going to write it. Now this actually bond is a sigma bond between, actually you know, to make it better what you can do? To make it better what you can do? Instead of this, draw it like this so that you can properly understand. I'm just drawing the hybrid orbital like this now, okay, because otherwise a lot of mess will get created, okay. So this is sp2, this is its sp2 and this is sp2 and this is sp2. This is also sp2 of other carbon, sp2 of other carbon. So can you see till now this thing is formed? These are sp orbitals, sp2 orbitals. So one sigma bond here, and here 1s and 1s is going to combine with the, is going to overlap with the sp2 orbitals, hybrid orbitals. This sigma bond is formed between sp2 and sp2 hybrid orbitals. This and this sigma bond is formed between sp2 hybridized orbitals and unhybrid orbital of hydrogen, that is 1s. Right? Now we have one thing remaining, that is your 2 py or pz, anything you can take, right? So that will show you a pi bond here, right? That will show you a pi bond here. So you can write this is pi, this is sigma, this is sigma, this is sigma, this is sigma and this is sigma. That's how you have 5 sigma, 1, 2, 3, 4, 5 and 1 pi bond, right? And that is sp2 hybridization. Okay? Okay guys? Clear everyone? Clear? Okay, right? So these sp orbitals, right, they are going to give you what? Trigonal planar geometry, right? Now let's talk about sp3. In sp3 what you will have? This is a mixing of one orbital, one s orbital with 3 p orbitals of valence shell to form 4 sp3. Now just understand what is sp, what is sp2, what is sp3, right? After that I'll tell you more things, right? The 4 sp3 orbitals are directed towards a tetrahedron. Now what is this shape? I'll just show you 3 shapes here because till now we have done only 3 shapes, right? Let's see, wait a minute. Guys, if I talk about this is a linear geometry, okay? This is shown by SP. If I talk about, let me just give me a minute. Okay. If I talk about this is a tetrahedral geometry that we are talking about for SP3. Okay. So till now you just see what it is. Detail we will discuss about later, right? Because next lecture is going to be on shapes only. Now if I discuss about trigonal, planar, that will be like this. This is your trigonal planar. In a plane you have a triangle kind of structure that is given by SP2. Okay, you just need to remember that, right? SP is linear, SP2 is trigonal planar, SP3 is tetrahedral, which has a 109.5 degrees angle. That means this angle here is 109. This angle here is 109. This angle here is 109. And you will see all the angles are same. If I place it here, it is same. If I place it like this, it is same. If I place it like this, it is same. So it is always going to be same. So all the angles here are same only, right? Okay. Now let's discuss the same thing in CH3 and CH3, that is sp3 hybridization. This will help you in organic chemistry also. So carbon is 1s2, 2s2, 2p3, right? In the excited state, it is 1, 2 and 3, and here it is going to be 1, 2. Excited I am writing, okay? Excited state will be like this. We are saying sp3 hybridization is having, okay? So this is 1s. See, only valence will participate, so these are valence orbitals, so it is going to form 3 sp3, because sp3 you have, and how, because 4, no not 3, 4 sp3, 4 orbitals are combining, so 4 will be formed here, right? Now let's understand this thing by making the structure. Let's understand this thing by making the structure. So when you make the structure here, it will be, this is carbon, right? This is carbon. Firstly, it is going to form 4 sp3 which are in the tetrahedral form, and we write tetrahedral form like this. Okay, so what I'll do, 1, 2, 3 and 4. Okay, 1, 2, 3 and 4. That's how I am drawing tetrahedral. Right? So we have tetrahedral. No p orbital is unhybridized. So what you will do? Hydrogen 1s, 1s, 1s will combine here. Right? And here all will be sigma bonds. Right? This is also sigma bond. This is also sigma bond. Now here all are sigma bonds. This is sigma, this is sigma, this is sigma, 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 sigma. All are sigma, but out of this 5 sigma bonds are between sp3 hybridization and 1s of hydrogen, and 1 sigma bond is between sp3 and sp3 hybridization. So these kind of questions also they ask, that in this compound how many bonds will be sp3 hybridized, how many bonds will be sp3 1s hybridized. So for that you should know how to draw the structure, right? Very rarely they can ask it, but simple structures only they will ask here, right? Okay, right, everybody got it, right? So here the situation for CH4 that we have already drawn. This diagram I have already shown you here as well, This is how it looks in 3D. Okay. Now, so that is about sp3 hybridization. Since the force of repulsion, a lone pair and bond pair is more than the force repulsion between bond pair of the electrons, the molecule get distorted and bond is basically this. Now we will not talk here, right? Wait a minute. This will not talk here because these bond pair, lone pair repulsions, everything will talk about in VBT and Vesper. Okay? In Vesper and VBT will talk about bond pair, lone pair, everything, every single structure. You are given a compound, but for that this knowledge is important, right? So now if you talk about this is I think they are talking about CH. This is not sp2. This is sp2. This is not sp3. This is sp2. Okay. So here we are talking about CH2. So this also I have already discussed, and I have also told you how to make this bond, right? Then in sp3, this is sp. Wait a minute, let me just correct it, guys. This is sp. Okay. This structure also we have seen, CH and CH structure we have seen. This is sp2. This also I have told you how to make this structure, isn't it? We have already seen this. Right, we have already seen this structure. Now show hybridization of CH4. This also beta we have discussed, so no need to discuss that again. Let's discuss this thing. This is actually what is useful in coordination chemistry, right? So in coordination chemistry, d orbitals are involved. The elements present in third period contain d orbitals. So if you have actually studied periodic classification, you must know that this is first and this is second period. In third period, you will have d block in front of it. So that means the third period elements will have d block, vacant d block or d orbitals also. The energy of 3d orbitals are comparable to the energy of 3s and 3p orbitals. The energy of 3d orbitals are also comparable to 4s and 4p. This is a very interesting point that we study in coordination chemistry, that we have sp3d2 and we also have d2sp3 hybridization for coordination number 6. What is the reason? Because this reasoning, assertion reasoning questions can be asked based on this, right? This is all these lines, important lines are from your NCERT. Right, the energy of 3d orbitals are comparable to 3s, 3p. In that case, what you will have? You will have, if you say 3d is formed between 3s and 3p. In that case, you will have the formation of d2sp3, and if you have 3d, wait a minute. 3d with 4s and 4p, then the answer will be sp3. Wait a minute, yes. No, opposite I have written, yes. Okay. So basically, if you have 3s, 3p and 3d, then it will lead to sp3d2. And if you have 3d, 4s and 4p, then it will give rise to d2sp3. That is why you have inner and outer octahedral complexes. However, since the difference in energies of this and this is significant, no hybridization involving 3p, 3d, 4s orbitals is possible. Okay, right? So it's not like you will have one 4s and one 3d and one 5p. This is not possible, right? Okay, either with these two set of pairs, 3s and 3p will always go together and 4s and 4p will always go together. Either this 3d will be linked with this one, then you will have outer octahedral, and here you will have inner octahedral, right? Now this is what we have discussed in coordination chemistry also, that do you remember when the coordination number is 4, right? When the coordination number is 4, you can have dsp2. Now this is basically when I talk about d orbital. sp, sp2 and sp3 we discuss about s and p orbitals. Can d orbitals also show hybridization? Yes, they can show. The hybridizations that are shown by d orbitals are like dsp2, which give rise to square planar geometry, sp3d, which give rise to trigonal bipyramidal, then sp3d2 and d2sp3 that gives rise to, wait a minute, sp3d2 and d2sp3, right? So this gives rise to your octahedral geometry, right? Okay, so these are the things that are possible here, right? Now this we have already discussed in coordination chemistry, but we'll discuss more about it, okay? So, but for that, one simple trick I'll tell you. Whenever a compound is given to you, you need to find the steric number. Once you know the steric number, from that, now you know the base of hybridization, that sp, sp2, sp3, dsp2, d2sp3, and then sp3d, all these can exist, all these hybrid orbitals exist. But to understand which compound will give which hybridization, and a specific hybridization is belonging to which set of shape and geometry, for that you need to understand this steric number, okay? So let's understand. So steric number is nothing but it is number of sigma bonds. This is what will be useful in your exam, okay? Till now I was just teaching you the base. So steric number is number of sigma bonds plus number of lone pairs. Sigma bond means number of bond pairs, plus number of lone pairs. That is your steric number. And each steric number has a specific hybridization designated, right? If steric number is 2, it is sp. If steric number is 3, sp2, 4, sp3, 5, sp3d, then 6, sp3d2. That's it. This is what you will use in chemical bonding, right? If steric number is 2, 3, 4, 5, 6, you have specific hybridizations, okay? So steric number 2, sp, 3, sp2, 4, sp3, 5, sp3d, 6, sp3d2, okay? sp, increase p, p2, this will be p3, then once you have p3, increase d, then add one more d, okay? That is how you're going to see this, right? So once you know this and they ask you, they give you some structure, calculate. Now this, how do you answer this? How do you calculate this from the Lewis dot structures? I already told you how to draw this. We have no idea what kind of geometry it is going to possess. Till now we just know that this is going to be the structure, okay? We don't know about the geometry. But one thing we know, that steric number, let's call it Z, that is equals to, bond pair is 3 bond pairs and you have one lone pair here, so it will be 4. So Z is going to be 4. That means it is going to be sp3 hybridization. And that is why I am only talking about the geometry. I am not talking about the shape. Shape and geometry is different, okay? So till today we are only talking about the geometry. Now I'll just write it here. Belonging to sp, you have linear geometry. Belonging to sp2, you have trigonal planar geometry, okay? Belonging to sp3, you have tetrahedral geometry. Belonging to sp3d, you have trigonal bipyramidal geometry. Then sp3d2 is nothing but octahedral geometry. So every hybridization is giving you different kind of geometry. Now guys, I'll just tell you what is all this. Linear is this kind of geometry. This is your linear geometry, right? This is your linear geometry which has 180-degree angles, linear geometry. Then you have trigonal planar. This is a plane and a triangle kind of structure is getting formed. This is sp2, okay? Now tetrahedral is, ma'am, dsp2, d2sp3 form. Yes, Darshan, they are formed, but in chemical bonding we don't discuss about that. Why? Because transition elements form these kind of structures. Okay, so that we'll discuss about in coordination chemistry. Right, I have already done coordination chemistry by the way, and there we will discuss about this. Now tetrahedral is this kind of bond. Can you see? This is tetrahedral structure. This is tetrahedral structure. Now what is trigonal bipyramidal? What is trigonal bipyramidal? You have trigonal planar. In this you should have two pyramids. One is above and one is below. That is trigonal bipyramidal. This structure is trigonal bipyramidal. Okay, this structure is trigonal bipyramidal. Now just let me just show you the octahedral structure. This we have already discussed so many times, okay. So many times we have discussed about octahedral. So firstly, those who know what is a square planar geometry, that though it's okay if you don't know. If you have not done coordination chemistry, it's fine, right? Because that we will not do today, okay. So here you have, wait a minute, this one, and this one. Just give me a second, and wait a minute, let me just draw that. Not draw, let me just make the structure. Yes, so this is your octahedral structure, okay. This is the octahedral structure that we will be discussing, right. This is the octahedral structure that we will be discussing, right. So you have like a square, you have at 90-degree angle, you have the bonds that are joined together, then one above and one below you have 90-degree angle. That is the octahedral structure, okay. Structures and geometry, we'll discuss about more about this in next class. Today I'm just giving you a introductory part of that. Now if in this structure they ask you what is the hybridization, now understand one thing, when you are calculating this sigma bonds, now these bond pairs are always sigma bonds. In steric numbers don't include pi bond. Don't include pi bonds here, right? You will not include pi bonds here. So if you see this here, steric number is going to be, this is 1, 2, 3, 4, 5. You have 4, 5, wait a minute, each will have its own. Let's say this is first carbon, let's say this is second carbon. For carbon number 1, Z is going to be 1, 2, 3, 3 sigma bonds. There is no lone pair, so it is going to be, Z is going to be 3, that is sp2. For carbon, we have already discussed that this will be sp2. That's what I told you, that how you will find the hybridization, that I will tell you, right? So carbon number 2 is this one. Again 1, 2, 3, 3 sigma bonds you have. So Z is going to be 3. Again this is also sp2. So this carbon is sp2 hybridized. This carbon is also sp2 hybridized. Okay, right? Okay everybody, it is going to release soon guys, soon, right? Okay, understood? Now what if structure is not given? What if you are like, ma'am, I don't want to draw Lewis dot structure, ma'am, structure is not given, I don't want to draw it. Now ma'am, tell me how to answer. Now we are making Lewis dot structure a zero thing, that we don't know Lewis dot structure. Tell us without Lewis dot structure how to answer. So another way of calculating steric number just from the formula is number of valence electrons on the central metal atom. On the central metal atom, how many valence electrons you will have, plus number of surrounding monovalent atoms, plus charge on the molecule, plus minus charge on the molecule, plus or minus charge on the molecule, divided by 2. If you have negative charge, you will add it. If you have positive charge, you will subtract it. Okay? Divided by 2, that is your steric number. Okay with the help of XeF2, XeF4, understand this thing. This is Xe. Xenon belongs to group number 18, so it will have 8 outermost electron. Clear? It will have 8 outermost electron, is it? Yes. Okay, valence electrons. Valence electrons will be 8, no? Wait a minute. Okay, xenon will have 8 outermost electrons, group number 18 will have 8, group number 17 will have 7, group number 16 will have 6, 15 will have 5, these are the valence electrons. That I think I told you in the first lecture, right? So xenon will have 8 outermost electrons. So now let's calculate the Z here. Z is going to be, more of this we'll talk about, Z is going to be 8, number of monovalent atoms is 4, there is no charge here, so total it is 12, right? Total it is 12, this is divided by 2, so it will be 6. Now for 6 what you have, this is sp3d2 hybridization. That means here it is going to be octahedral geometry, right? It is going to be octahedral geometry. So what you will do, this will be xenon, this will be fluorine, this will be fluorine, this will be fluorine, this will be fluorine, and here you will have 2 lone pairs. So basically what you are doing here, in this case you are saying that you will have 4 sigma bonds with fluorine that I have drawn here with white. White is the fluorine atom and these green are the lone pairs, and here you will have 1 lone pair above, 1 lone pair below, right? Okay, so till now I am just telling you the geometry here. Shapes we are not talking about today, right? That we'll talk about tomorrow, and we'll discuss a lot of structures also. So geometry is going to be octahedral. Geometry is going to be octahedral. So similarly, if you talk about ClF3, chlorine belongs to group number 17, so 7 outermost electrons. Z is going to be, till now just understand the hybridization. So Z is going to be 7 plus 3 monovalent electrons, so it is going to be 10. 10 by 2 it is 10 by 2 it is 5. 5 means sp3d, that is nothing but trigonal bipyramidal. Trigonal bipyramidal, right? Okay. Now if you draw the structure here, right, when you draw the structure, it should be trigonal bipyramidal, because only 3 bonds it can form, so it will be Cl. It should be trigonal bipyramidal, looks like this. 3 sigma bonds only it can form. Rest should be lone pair then. Rest should be lone pair then. Right? Rest 2 should be lone pair. I know that still you are finding it difficult, right? I know that. See, actually till now, even if you understand only till here, okay, you don't understand how to draw the structure, it's fine, because this lone pair repulsion, bond pair repulsion, how to calculate lone pair, this we'll talk about in the next lecture, right? Around 30-40 structures I am going to draw in front of you, right? So that you don't have to worry about that, right? So we are going to discuss about that. A lot of questions we'll discuss about. Till now, if you're able to understand just one thing, that a formula is given to you, how to calculate steric number, and from steric number how to calculate the hybridization, and from hybridization what is the geometry. If you can remember the geometry related to the hybridization, that's it. Okay, for today, if you're not able to draw this, it's fine, it's fine. If you remember just till here, it's fine. Okay, today your target was only till here. To understand the hybridization, calculate steric number, right? It means the crux of today's lecture is, wait a minute, not this, we'll talk about later in next class, right? Yes, I'll just show you this question here. So question is given to you, that is SO2, NO2 negative and N3 negative is given to you, right? So what I'll do, one by one I'll calculate this, okay? SO2. You have no idea, ma'am, Lewis dot structure, ma'am, I don't want to draw that. JEE 2025 question. Till now, we are not discussing VBT, Vesper, we have just discussed hybridization, steric number, that's it. Now, SO2, NO2 negative and N3 negative. You just know that these are the three things that is given to you. If you know how to calculate Z, you will be able to answer this. Z is nothing but a center metal atom. Firstly, identify that center metal atom is sulfur. It belongs to group 16. So 6 is the valence electron. Is there any monovalent atom? No. So it will be 6 by 3, 6 by 2, that is 3. There is no positive negative charge, so it is going to be 3. That means it is going to be sp2 hybridized. Simple. Z is, nitrogen is the center metal atom. Here, in the center metal atom, it belongs to group 15. It belongs to group 15, right? So it will have 5 valence electrons. No monovalent atom. You have monovalent means either hydrogen or halogens. That is monovalent. Monovalent, you don't have any monovalent atom here. So what you will do, you will just add here, you will just, negative charge always is added, divided by 2, and that is 3. So it is going to be sp2 hybridized. For nitrogen, what you have? Let's say nitrogen is the center metal atom that is having 5 valence electrons, and there is no outermost electron here. There is no monovalent atom here. So you will add plus 1 divided by 2, that is again 3, that is again sp2 hybridized. Right? Wait a minute, will this be sp2 hybridized? This will be actually, if you see this, monovalent is 5, right? 1 is added here, 6 divided by 2, nitrogen 2 are added here. Some sort of 6 plus, that is belonging to 5, wait a minute, the answer, yes, it will be sp now. This is because this is sp hybridized, wait a minute, why? This is sp hybridized, from structure it is sp hybridized, okay. So, because of the coordinate bond, yes, because of coordinate bond, okay. So this is actually a exceptional case here, not exceptional, this is actually, when you see the structure now, this is coming out to be wrong with this steric number. I'll tell you why. Because in N3, you also have a coordinate bond here, right? You also have a coordinate bond here. The extra lone pair is actually being donated, right? That is the reason here, right? You will have sp hybridization if you see it from the structural point of view. This nitrogen has only 2 sigma bonds. We have calculated it to be sp2 because we considered that there will be some lone pair here. But lone pair actually will be donated in this case, right? There will be a coordinate bond. Because of that coordinate bond, because number of coordinate, for example, I talk about NH4 positive. Right? Now, because of that coordinate bond, what will happen, right? It is going to become like one, instead of sp2, it will be sp hybridized, right? So, that's why this is going to be sp2 and sp, that is D is going to be the correct answer here, okay? Understood everybody? So, Lewis dot structure, important, because in some structures like N3 negative, right? So you need to understand that if there is some coordinate bond, things will change there, right? Otherwise, this is valid for most of the structures, right? And now the conclusion is that you should remember this thing, okay? For next class, you should remember this thing, because next class we are going to complicate things more, right? We are going to take big structures. We are going to also focus on lone pair, bond pair, repulsions, shapes we will discuss, how because of these repulsions, these geometries will change, right? So all these things we are going to discuss in the next class, right? But for that you should remember this thing where it is linear, where it is, firstly you should know how to calculate, because for simple, see one thing you will say, ma'am, but steric factor is giving us NS3 negative, ma'am, it is giving us wrong, right? So N3 negative, these are what you draw from Lewis dot structure also, from there you can do. But from these kind of structure like XCF4, right, XCOF2, these kind of structures, right, BRF3, right, BF3, then BeCl2, these kind of structures we can learn from the VBT Vesper theory, okay, right, okay. So Vesper theory is going to tell us about lone pair, bond pair, repulsions. From there we will discuss about shapes. Firstly, from VBT we will discuss more in detail with different kind of structures. Okay? Yes, everybody? So that's it for today, and before going, guys, this is your homework, right? You can see which type of orbitals undergo hybridization. This is the first question for your homework, right? Second question is identify the incorrect statement about hybridization. This is the second question for your homework. Incorrect statement you have to identify from this. And before going, guys, first thing is happy Teachers Day to all of you as well, and you guys, thank you so much, Pritija, Shashank, then yes, that will be released, Malini, Siddesh, thank you so much, right? So this is today is a big day, and one thing that we all teachers want from you, what is the gift that you can give us? First thing is take your studies seriously, right? Because as a teacher it makes us really happy that you guys are doing something in your life, right? That you guys are not just casually taking studies and thinking, okay, whatever will happen. When we give you homework, do that, right? When we ask you to give this MVSAT program, then do that, right? Register yourself, because what will happen, you will actually question yourself that at what level you are. And what if you get into this 2.5 lakh students, you will get 150 crore worth of scholarship and 2 crore worth of prizes you will get, right? So these are the things that you will get. So as teachers, we only give you advices which are beneficial for you, right? And please take your studies very seriously, because this time is not going to come again, right? Now you don't have any responsibility, all you have to do is your studies, right? And if you're pro at it, you will be good in all the responsibilities that future will give you, right? So that's it for today, and students, till then, bye bye, take care, and do register yourself to this MVSAT program. The link is in the description. Till then, bye bye, and tomorrow I'll see, maybe at 6 p.m. I'll take the class. So at 6 p.m. tomorrow, we are maybe 6 or 6:15 p.m., right? I'll start with VBT and Vesper. Okay? Yes, everyone? Sure. Okay then, bye-bye. Take care. See you all in the next class. Bye-bye.